Is there any doubt or okay, attempted and no doubt. Okay. Gayatri,
Yes,
do you have any doubt?
attempted and no doubt
Okay.
was able to solve those.
Okay. So this was easy portion. This propositional logic. This is actually just similar to Boolean algebra that we study in digital logic or computer organization. So these propositional logic is also a kind of algebra. So they are quite similar. It's just that names are changed. Like here we called that conjunction operator, and in Boolean algebra we call that and operation and gate. Okay, so these kind of differences are there. And Boolean algebra, in Boolean algebra, when you will be studying computer organization or digital logic, these kind of subjects, so at that time also you will be again studying these things of propositional logic. Okay, here we call the truth values are true or false. Okay, there what will happen, the true will become 1 and false will become 0. So not much difference, both are exactly same. So okay, we will start. Okay, still 2 minutes are so we have seen this precedence of logical operators. Okay, so basically sometimes what we should do actually, that we should properly parenthesize our expressions. In mathematics also you have seen like multiplication is given higher priority than addition. So if we have an expression like for example, let's take, yes. So for example, if we have expression like 2 plus 3 multiplied by 4, then what we do, then by default what we assume is that because this multiplication has higher precedence than this addition operation, so then what will we do, basically we first compute this multiplication, and then we compute this addition, so it will be, and it will become 14. Okay, so assume that what would happen if this addition operation had higher precedence, then what would happen, then we would compute this addition first, so it will become 5 multiplied by 4 and it will become 10. So you can see that different precedence can lead to different results. So that's why this precedence order is also important. Okay, so in this propositional logic we have this is the standard this precedence of logical operators. Okay, so we have this unary operator mostly actually in even in C programming language. You must see that these unary operators actually are having higher precedence than binary operators. Then we have this conjunction, disjunction, implication by implication, and so on. So these kind of things we have already seen. And okay, now it's time. So if there is anyone who will be joining, I think so we should start now. Okay, let's see this. So first I will discuss some things about truth tables. Okay, so what are truth tables? We have already discussed. So basically truth tables tell us about the behavior of a operation. For example, we have already made truth table for conjunction, disjunction, implication, these operators. We have already seen truth table. So for these operations, the truth table tell us the behavior of those operations. For example, if we have a truth table for this implication operation, then we have seen that okay, how this implication operator, how this behaves. Okay, so basically if P is true and Q is false, then this whole expression becomes false. Else in all other cases, when either P is false or Q is true, in all those cases basically this P implies Q, this expression becomes true. Okay, so this is basically the idea of truth table. So if we have an expression, if we have any expression, for example, if I give you any expression P plus Q, this plus is nothing but the disjunction operation. Okay, so P plus Q, or this is conjunction operation, this R, and let's assume bar. So P plus Q and conjunction and then R bar. So for this expression, let's call this expression f. So for this expression f, we can make a truth table, so that that in this expression we have three propositional variables. There is p, there is q, there is r. So we have three different propositional variables. So in truth table for this function f, we will have how many columns will be there. So basically we will have one column for each propositional variable. Okay, so there will be three columns for pqr, and there will be one column for the expression or the function itself. Okay, so now since we have three propositional variables, so now how many rows are possible, we have already discussed it in the last lecture. So how many rows will be there? We know that every propositional variable can either have 0 or can either have 1, right? 0 means false and 1 means true. So every propositional variable can be assigned either true or false. So basically for every propositional variable we have two possibilities. For p also we have two possibilities, for q also we have two possibilities, and for r also we have two possibilities. So total 8 possibilities are there. Okay, so for example 0 0 0 0 0 1 0 1 0 and so on, 1 1 1. Okay, so total 8 rows uh, in this truth table. Now since this f is a function, this f is a, you can see, a proposition. This f is also a proposition actually. We have, because we have already discussed that if p is a propositional variable, then we can if pqr are propositional variable, then using these connectives, these plus this conjunction, these are also called connectives. Okay, so using these connectives we can make new propositions. So basically if we have a proposition p q, and if you have a proposition r, then this whole thing means this f is also a new proposition. This is a new proposition that we have created out of p q r. Okay, so now this proposition also will have these one of the truth values. For example, it can be either 0 or it can be either 1, for example, depending on the values of pqr. Okay, so for example, if pqr all are false, then what will be the this value of this truth value of f? What so if p is false and this q is also false, then what will happen? This complete thing will become false, and the truth value of f will become false, right? So similarly, so for each row, for each row we can we can easily find the truth value of f. Okay, how can we find? So basically f is nothing but p plus q conjunction r bar. Now for example, this row, this 0 0 1, this means that propositional variable p is assigned false, propositional variable q is assigned false, and propositional variable r is assigned true. So for this assignment, what will be the value of f? So if p is false and q is false, then automatically what will become? So p is false, q is false. Since q is false, so conjunction, the behavior of conjunction operation is such that this whole expression will become false. Now if this is false and this is false, so this disjunction operation also will become false. So the truth value of f for this assignment, okay, for this row 0 0 1 also will become 0. Okay, so similarly for other rows we can find. Okay, for example, let's find for this row 0 1 0. So basically p 0, q is 1, and r is 0. So for this row, so p is 0 and q is 1 and r is 0. Since r is 0, so r bar will become 1. Okay, q is 1, so this and this conjunction will become 1. Okay, now since the disjunction operation is 1 when at least one of its one of its operands becomes 1. So if this thing is 1, then the value of the truth value of f will be 1. Okay, so similarly we can find that truth value of f for all these 8 cases. Okay, so this is basically the idea of truth table. Let's see what is this theory. So basically any proposition can be represented by a truth table. Okay, so if we have a proposition, then we can make a truth table, and that truth table will tell us the behavior of that proposition basically. Okay, so now it shows truth values for all combination of its constituent variables. So basically if we have a proposition or that has three variables, for example here f is a proposition that has three propositional variables. Okay, so now the truth table for f will tell us about the truth values of f for all the combinations of pqr. Okay, so now propositions, for example here if we have a two variable proposition. Okay, if we have two variables p and q, and if we make a function, if we make a propositional function out of these two variables, then the truth table will have how many rows? We have already discussed this thing, so it will have four rows. Okay, so for all the different combinations, for example p true q true, p true q false, p false q true, and p false q false, so these are all the different combinations that are possible. So we have one row for each combination, and for each combination what we can do, we can find the value of our propositional function. For example here we had considered the propositional function f. Okay, similarly you can I can give you any propositional function that that is made out of these p and q propositional variables. So you can easily find the truth values of these are using the truth values of these propositional variables p and q. Okay, so let's see okay, so basically let's see one variable truth table. Okay, so let's see one variable truth table. So with one variable, if I have only one variable, for example p, then okay, I can make a truth table like this. So how many rows will be there? How many rows will be there? If there is only one propositional variable, then there are only two combination, either it can be 0 or it can be 1. Okay, so this is 0. Okay, now either it can be 0 or it can be 1. Now now how many, so basically this will be the structure of the truth table. Okay, for any function. For example f is a function, f is a propositional function. Okay, that only includes this one variable, that is okay p. So how many rows will be there? There will be two rows. And how many functions can we make? For example we can make here four functions. How? One function is 0 0. Okay, so this is one function. Now another function we can make is 0 1. Another function we can make is 1 0, and another function 1 1. So you can see there are only four functions possible. These all are different functions. You can see, for example this is 0 0 and this is 0 1. So basically you can see in this case, okay, these two functions, if I call this f1, if I call this f2, and let me call this f3, and let me call this f4. So you can see that these f1 and f2 are different. And how are they different? You can see that, okay, when p is 1, at in that case f1 is 0 and f2 is 1. So you can see that, okay, f1 and f2 are different. Similarly you can see all these four functions are mutually different. You can see, you can pick any two of them and they are different. So you can see if we have only one variable, then how many rows will be there? There will be 2 power 1 rows. Okay, in the truth table. And for one variable, how many functions will be there? How many propositional functions we can make? So you can see there are four functions are possible. How they are four? So you can see for each row, okay, you have two possibilities. Okay, for example if for this row, okay, for this row you have two possibility. Either you can assign 0 or you can assign 1. Okay, because this f is also a propositional function. Okay, so for any assignment of propositions, okay, it will assume either false or true. Okay, so basically there are two ways in this for this row, and there are two ways for this row. So total will be four. So how many ways are there? So total four ways. So how many functions we can form? So there are four functions. These are propositional functions. Okay, so with one variable we have two rows, and with one variable we have four functions. Okay, now let's solve it for two variables. So okay, we have seen this. Now uh, so let's solve this thing for two variable truth table. So for two variables, if we have two variable, let's assume they are p and q, then how many rows will be there? For two variables we know that, okay, there are two ways for this, there are two ways for this, so there will be 4 rows. Okay, so there will be 4 rows, for example r0, r1, r2, r3. Okay, r2, r3. So there will be 4 rows in this in this truth table. Okay, for any function. Okay, basically if there is a propositional function, okay, that involves only two variables p, q, then for that function if we make a truth table, then that truth table will only have 4 rows. Okay, so now how many propositional functions are possible, how many different propositional functions are possible for these two variables? Okay, can you tell me? You see that for this row we have two ways. Okay, for this row also we have two ways. What are these two ways? For example, for this row, okay, for some combination of p and q, let's assume p is false, q is false. Okay, that is a combination of p and q. So for that combination we know that this function value either can be 0 or it can be 1. Okay, so there are two ways. Okay, so similarly for this row also we have two ways, for this row also we have two ways, and for this final row we have two ways. So finally how many ways are there? 2 power 4. Okay, so basically okay, let's we will try to derive a formula for a general case when there are n propositional variable. Then for n propositional variable, how many rows will be there in the truth table, and how many propositional functions are possible on n on n propositional variable? We will find that. Okay, so I would like you all to solve the question for three propositional variable. Okay, so before that, okay, this is the basically we have seen all these truth tables already. So you know that this not gate, so basically this is a unary operator, so this takes only one proposition as an argument. So basically if p is a proposition, then we know that okay, this p bar is the negation of p. So this only takes one variable. So basically this not gate truth table will only have two rows, and okay, this is the truth table for this not operator, this negation operation. Okay, so similarly we have already seen this and, or, and xor. Okay, so okay, let's try for three variables. Okay, so think about how many so there are two questions. Okay, how many rows are possible, how many rows will be possible? Basically each row is a different combination. Okay, if we have a propositional function on three variables p, q, r. Okay, so the question is that, okay, let me write a question, and then okay, you can try to solve it. So if we have a propositional function f, okay, and that propositional function f has three that function involves three propositional, okay, variables p, q, r. Okay, then your question is how many so basically your question is how many number of rows are possible in the truth table. Okay, so basically in the in the truth table. Okay, truth table. So how many rows will be there in the truth table, and how many number of different these propositional functions possible? Okay, so these two questions, okay, you try, and okay, let me give you 30 seconds, maybe you can try. Okay, Sanjeev, yes. Okay, Bhavya, yeah, I just saw your message. Yes, I'll go slowly. Are there any rules for creation, sir? I did not get your doubt, Vasam Seti, Santosh. Can you speak, and can you tell me what is your doubt? You can speak if you want to. There is no problem. For creation of proposition, proposition is just just a declarative statement that is either true or false. So uh, we can take we can join different propositions, and we can make compound propositions using those connectives. For example, if we have two propositions, okay, one proposition is my name is Deepak. Now this is one proposition, and the next proposition is I am 25 years old. Okay, these are two propositions. Okay, now we can join these two propositions and we can make new propositions. For example, if we join these two propositions using and connective, okay, which is also called conjunction, then we will get a new proposition, and that proposition will be my name is Deepak, and I am 25 years old. Okay, similarly, if okay, is your doubt clear? Similarly, you can use other other connectives. Okay, for example, if you use this implication, okay, we have already seen this implication operation. So if you use that implication operation to join these propositions, then one new proposition can be made, and that will be, if my name is Deepak Punia, then my age is 25 years. Okay, so these kind of new propositions we can create. Okay, so yeah, Sanjeev, Bhavya, right? Yes, there will be 8 rows. Okay, and there will be 256 different functions. Okay, so now let's just quickly write a general formula. Okay, for n variables. So basically, let's write a okay, yeah. So if we have if we have n variables, for example, let's assume a1, a2, and so on, n. Okay, an. So basically, if there is a propositional function, okay, if there is a formula, if there is a propositional function that involves n variables, okay, then how many different propositional functions we can create? So so for that, what we can do first, we can find how many different combinations are possible for these n variables. So you know that for each variable we have two choices. So basically there will be 2 into 2 and so on. So basically there will be 2 power n different combinations possible, okay, for n propositional variables. So there will be 2 power n rows. Okay, there will be 2 power n different combinations. Okay, so now so we can, for each of these combination, okay, if we have these okay, these, for example, this is these 2 power n combinations we have, and for each combination we can have either true or false. Okay, so basically we have two possibilities. For each combination we have two possibilities. So basically now if we multiply them, then we will get the total number of, okay, different proposition functions that we can create in that involve n, okay, propositional variable, and that will be 2 power n, right? So this is the final formula. So if there are n propositional variable, then we will have 2 power n rows. So this 2 power n is for number of rows. This is for number of combination, different combinations. Okay, and this so 2 power, this 2 power n, and this whole thing is basically number of different propositional functions that we can create on n variables. Okay, so okay, let's take this example as well. So if we have this if we have this propositional function, okay, so basically this propositional function is involving three variables, p, q, r, and try to construct a truth table for this quickly. uh, you have around I think 30 seconds, 1 minute will be enough. Try it. Construct the truth table for this this propositional function. You can create few rows, if not all 8 rows, maybe just 3 or 4 rows you can you can try, and then you can see, you can verify your answer. Okay, so Sanjeev is done. Okay, so I think, okay, let's let's do this. So since this propositional function has this is involving three propositional variables, so we will have 8 different combinations for these variables, this p, q, r. We will have total 8 different combinations. Okay, so we can write them like this: 0 0 0. Okay, so this means that, okay, p is also false, q is false, and r is false. So this is one combination that is possible. Similarly, there are 0 0 1, okay, 0 1 0, for example 1 0 0, sorry, 0 1 1, and 1 0 1 1 1 0, and then 1 1 1. Okay, so basically, actually, how you can write them quickly if if you write them like this. This basically, this 0 0 0 is nothing but the boolean representation of the decimal 0. So if I have a decimal number 1, then this is the boolean sorry, binary representation of that 1. So if I have decimal 2, then this is the binary representation. Okay, so the third row, actually, okay, this will be the fourth row. So basically, this will be the third row. So for 3, we can write 0 1 1. This is the binary representation of this 3. And similarly, then there will be next row, that is 1 0 0, and then 1 0 1 1 1 0, and 1 1 1. These things, you will be studying in boolean algebra. Okay, you will be frequently using these things. Okay, so now, for this combination, what will be the value of this function? So since p is 0, so what will happen? This will become this not p. Okay, this not p will become true, and we don't need to compute any further, because this disjunction operation, actually, its behavior is that if one operand is true, then it will become true. So basically, this will be true. So basically, wherever you can see p is false, then you can directly make it, okay, true. For example, here p is false, p is false, p is false, p is false. So okay, okay, all these rows, you can directly write 1 1 1, because this propositional function will become true. Okay, so similarly, you can fill, okay, for other rows. So that is how you can construct truth tables. Now let's move on. uh, yes, so next topic is translating English sentences. Okay, let's translate these sentences into propositional functions. Okay, uh, so you have this statement: you cannot ride the roller coaster if you are under 4 feet tall unless you are older than 16 years old. And let's assume that these three statements are, for example, uh, this, okay, this q, actually, this q represents you can ride the roller coaster. Okay, this r represents you are under 4 feet tall, and this s represents you are older than 16 years old. Okay, then so for this statement, okay, what will be the corresponding logical expression? What will be the corresponding expression in propositional logic? Okay, you can try it, then we will see the solution. Try it. Okay, can you again this statement. I did not get your doubt, Bhavya. Okay, say question again. So okay, let's also solve this. Okay, you can try the next question. So basically the question is that you have this English expression. Okay, this English expression is this English sentence is that you cannot ride the roller coaster if you are under 4 feet tall unless you are older than 16 years old. Okay, so this is English sentence. Okay, now what we want to do, we want to convert this into propositional logical expression. Okay, now so to convert them, okay, you need propositional variables that represent these individual sentences. For example, this you cannot ride roller coaster. Okay, now this is one statement. Okay, now we can represent this statement using a propositional variable. Then you have the next statement, that is you are under 4 feet tall. Okay, now this is another statement, and this is another proposition, and we can we can represent this using another propositional variable. And similarly, you have this third statement. Now this third statement or this third proposition, you can represent this using another propositional variable. And then once you have represented these individual propositions using propositional variables, now you need to write the expression for for this whole sentence. Okay, so what we have done, we have given that q is you can ride the roller coaster. Okay, since q is you can ride the roller coaster, so what will be the expression for you cannot ride the roller coaster? So for this you cannot ride the roller coaster, for this the expression will be q bar, right? Because q is you can ride the roller coaster. Okay, so if I want to write you cannot ride the roller coaster, then the expression will be q bar. Okay, now this you are under 4 feet tall. Okay, you are under 4 feet tall, this is as it is. Okay, this is represented by r. Okay, so basically this proposition is represented by r, and this last proposition, you are older than 16 years old. Okay, this you are older than 16 years old, this is represented by s. Okay, now basically you can think like this, you can convert this whole English sentence into like this. You can write like this: q bar. Okay, q bar if r, q bar if r, unless 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 this s. Okay, so basically what we have done, we have converted this English sentence into this sentence: q bar if r unless s. Okay, now we can convert this again. So what we can do, that this unless is nothing but, we have already we have already told this in the last lecture, that this unless actually behaves like plus. Okay, disjunction. Okay, so now for this we can write like this: q bar if r. Oh, and I have already told that this if actually goes backward. Okay, in the last lecture in the we have already discussed these things. So basically this q bar if r, this will become r implies q bar, right? And this thing plus s. Okay, now you might have gotten some other answer. Okay, some other answer, because whatever answer you have gotten, if that answer is equivalent to this answer, then your answer is correct. Okay, because you know that this expression can be written in many other ways. Okay, many other equivalent ways. Okay, so for example, I've given the answer like this. You can see I have given the answer like this. Okay, and in the last I have just said that the one other answer that is possible, that is okay, what was that answer? That is R implies Q bar plus S. R implies R implies Q bar plus S. Okay, now I I leave it up to you to verify that this expression and this expression, basically these are equivalent. Okay, so if you have gotten this answer, then your answer is correct. Also, if you have gotten this answer, then also your answer correct is correct. And if you have gotten any other expression, okay, and that expression is equivalent to this expression or this expression, then also your answer is correct. Okay, how you can verify that these are equivalent? You can make truth table for this, also you can make truth table for this, and you can check that the truth table for this will be same, exactly same as truth table for this. Okay, or how can you try, okay, how can you check this? Okay, without writing the truth table, you can check like this. So what will be this? This we have already told you in the last lecture that this P implies Q. This can be written like this: P dash plus Q, right? P dash plus Q. So similarly here, this implication, I can remove this implication, and what will I can write like this. For example, this R and S bar and this whole thing bar plus Q bar, right? Okay, now what will be here, you can use the De Morgan formula. In the last lecture we have already discussed this. So this will be R bar plus S plus Q bar. Okay, so you can see this is the expression that we have gotten from this. Okay, now what will be the expression for this? So this will be again, this you can remove this implication, and this will become R bar plus Q bar plus S. You can see both are same. Okay, so basically these two expressions, these two actually are they seem like different expressions, but you can see they are equivalent. Okay, so if you have gotten this answer, then also your answer is correct, and if you have gotten this answer, then also your answer is correct. And assume that in gate exam such question is asked, and you have four options, and assume that you get some answer. Okay, you get some answer A1. Now assume that your the answer that you got is not matching with any of the four options that are given. Okay, then what you can do, you can just check if your answer is correct. If you are confident that your answer is correct, then you can just check which of the options is actually equivalent to your answer. Okay, and whichever option is equivalent, you can just answer, you can tick that option. Okay, so I hope this problem is clear. Okay, now uh, Sanjeev, R and negation S implies Q. Okay, this is the answer you have gotten, right, Sanjeev? R, are you saying that? Yes, yes. Yes. So what the answer that you have gotten is this. Okay, and you can also get this answer okay, by this method. Okay, but both answer are same. Okay, so your answer is correct. But there are there are many different ways, okay, to write the same expression. Okay, all these expressions are equivalent. Okay, so there is no one fixed expression that that is the correct answer. Okay, but all the equivalent expressions are correct. Okay, but if you have gotten some expression that is not equivalent to these expressions, then your answer is incorrect, and you can check why that is the case. Okay, so let's take one more example, and then we will move to the next topic. So let's take one more example. uh, yeah, okay, try this. Bhavya, try this. If you could not attempt the previous question, then so here we have a English sentence. You can access the internet from campus only if you are computer science major or you are not a freshman. Okay, and we have given some propositional variables for the individual propositions that are present in this English sentence. Okay, there are three propositional variables I have given. There is A, and A is for you can access the internet from campus. Okay, so and C is propositional variable for the proposition you are computer science major, and F is the propositional variable for the proposition you are a freshman. Okay, now using these three propositional variables, you need to write the expression for this sentence. Okay, so okay, now let's see, you can check if your answer is correct or not. So let me now basically this sentence is okay, you can access the internet from campus. Okay, now this basically this proposition is okay denoted by A, and so basically what we can do, we can write like this: A only if you are a computer science major, that is C. Okay, sorry, let me not write like this. Or you are not a freshman. Okay, since you are a freshman is F, then you are not a freshman will be F bar. Okay, now basically what you need to do, A only F, and the statement is like this. Okay, so so the answer, you know that I have already told you only if. Okay, there was a trick I have told you that only if actually goes forward. Okay, so that is a trick. Actually this trick is really important because it saves you time. Okay, but we have already seen how it works. Okay, we have already seen in the last lecture, but it saves you time. Okay, so this will become this or is nothing but conjunction, and this is F bar. Okay, so this is the answer you should get. Let me see if you have gotten this. So exclusive or, okay, okay, Gunaskaran, you have actually used exclusive or. Yeah, right. Actually, in discrete mathematics, unless it is unless it is explicitly mentioned, okay, that you need to use exclusive or, okay, this or actually means inclusive or. Okay, this or means inclusive or. Okay, so basically you should not write exclusive or for this. Okay.
Okay.
And I think what you have so yeah, right. So basically remember this, that in logic, in mathematical logic, in propositional logic, or in first order logic, this or by default means inclusive or. Okay, inclusive or means this disjunction. Okay, this
Okay.
exclusive or you will use when it is explicitly mentioned that okay, this is exclusive or. Okay, now A implies C or negation F. Sanjeev, correct. A implies C or negation F. Gayatri, correct. Yeah, right. Okay. So let's move. So I think these translations are clear. Okay, I'll give many practice questions for this, because around 10 or 15 practice questions I will give, and you can try them. Okay, so for now we will move to the next topic. Okay, so yeah, this is the answer. Yeah, next. Okay, so now this, okay, this we have already seen actually, but for the purpose of this, for the completion of these slides, I have already put it here also. Basically what it is saying that, okay, in Boolean algebra, basically this slide actually is nothing but the comparison of Boolean algebra and propositional logic. Okay, you know that, okay, let me write a comparison of propositional logic and Boolean algebra. Okay, completely. So basically this side I will write what we do in propositional logic, and this side I will write what we do in Boolean algebra. Okay, let's do some comparison. Okay, so basically in propositional logic, we know that there are two truth values. Okay, there is one is true and there is one false. Okay, so corresponding to this true in Boolean algebra we have one, and corresponding to this false we have 0. Okay, similarly in Boolean algebra we have, okay, conjunction operation. Okay, in Boolean algebra we call it conjunction, and in sorry, in propositional logic we call it conjunction, and in Boolean algebra we call it uh, and operation. Okay, and operation, and it is the operation of and gate. Okay, so in propositional logic we have disjunction operation, and in Boolean algebra we have or operation. Okay, so similarly in propositional logic we have this negation operation, and in Boolean algebra we have complement. Okay, we have complement, for example a bar. Okay, so now so these kind of things. Okay, so yeah, similarly all other things are some things are for example exclusive or. In propositional logic also we have exclusive or, and in Boolean algebra also we have exclusive or. Okay, in propositional logic we have this double implication, which we call a double implication or biconditional, we have already seen. In Boolean algebra the corresponding operation is XNOR. XNOR. Okay, XNOR. So sorry, XNOR. Okay, XNOR. XNOR. Now in propositional logic we have this implication operation, and actually there is no standard operation in Boolean algebra that corresponds to implication operation. Okay, so in propositional logic actually mostly this implication operation we use in discrete mathematics, or so basically this operation we have. Okay, now corresponding to this implication operation in Boolean algebra we don't have some standard operation. Okay, but they can explicitly define. But if we talk about the standard Boolean algebra, then there is no corresponding operation. Okay, in propositional logic we know that there is NAND operation and there is NOR operation. So corresponding to NAND operation in Boolean algebra we have, okay, we have a NAND only. Okay, there is a NAND gate, and in Boolean algebra we have a NOR gate also. Okay, so basically this is the comparison of propositional logic and Boolean algebra. You can see this, that propositional logic and this Boolean algebra, they are very similar. Okay, it's just the symbols are changing. Okay, the meaning is same. Okay, the behavior is same, the truth table is same. For example, the truth table for conjunction, okay, in propositional logic it's same as the truth table of this AND operation in Boolean algebra. Okay, so yeah, now let's take so okay, what was that previous slide? In this slide you can see one thing. Okay, so basically I have written these things because this Boolean algebra, this propositional logic is actually mathematical concept. Okay, but this Boolean algebra is widely used in computers. So in basically in computers you represent the information using bits. Okay, bits are nothing but 0 or 1. Okay, now so we have already written this thing true, and this 1 represents true and 0 represents false. Okay, so in Boolean algebra we call a variable Boolean variable. Okay, and in propositional logic we call a variable propositional variable. Okay, so these are the truth table. You can see that in Boolean algebra we have the for example this these are actually for example this disjunction. This is the truth table for disjunction. Okay, now in Boolean algebra you can see that the same truth table will be for x plus y. Okay, x or y. Okay, so this is just the slide for the for the sake of completion of slides, so that you can refer again. Okay, now let's solve this question. So you have this string. Okay, string is nothing but the sequence of bits. Okay, 0 1 and so on. So basically you have this string 0 1 1 0 1 1, then you have 0 1 1 0. Okay, and you have 1 1 0 0 0 1 1 1 0 1. Okay, so these two strings you have. Okay, now what you need to find, okay, you need to find the bitwise OR. So basically what you need to do, you need to do bitwise OR. Okay, you will perform the OR operation between these two bits, then these two bits, then these two bits, and so on. So you need to write the result of bitwise OR, bitwise and bitwise XOR. Okay, so try it. It's a simple exercise. You have 30 seconds, you can try it. Yes, okay. So the answer, you can verify your answers. Let's first answer the bitwise OR. So what will be the answer for bitwise OR basically? So you know that this OR operation, we know that if one operand is at least one of them is one, then the answer will be one. So for example, here answer will be one, here one, then one, then one, then one, then one, then zero, then one, then one, and then one. Remember that this 1 plus 1, okay, this is 1 actually. Why? Because we are not doing the binary addition. Okay, if you have already studied digital logic or computer organization, okay, then there are two different things. For example, this 1 plus 1. Okay, now if you are doing this, if this plus is nothing but the or operation, then the result will be 1. Okay, but if you are adding them, okay, binary addition, okay, if you are adding them, then it will be 1 0. Okay, so these kind of things. Okay, but I don't want to confuse you. Okay, so I just if you have studied this digital logic or computer organization, then there we have two different concepts. There is one concept is binary addition. Okay, where we add things. Okay, but this is actually a here we are talking about or operation, and operation, XOR operation. These are boolean operations. Okay, so their result is either true or false. Okay, so basically their result is either 1 or 0. Okay, so this is the difference actually. Okay, when you will be studying digital logic or computer organization, at that time also you will see these things. Okay, so now this is the operation, this is the answer for bitwise or, and similarly you can write answer for bitwise and. You know that and is true only if both are true. So for example, in this case it will be true. Okay, or in all other cases, so similarly in this case also it will be true, and in this case also it will be true. In all other cases it will be false. Okay, now you can write the answer for bitwise XOR. So if you remember the bitwise XOR, it is exclusive OR. So basically it is true when exactly one of them is true and other is false. Okay, so for example, for this row, okay, 0 1. Okay, you can see this 0 1. So here the exclusive OR will be 1. Similarly here both are 1, so it will be 0. Similarly here one is 1, the other is 0, so it will be 1. Similarly both are 0, so it will be 0, and so on. Okay, you can try this. So you can see the answer in the next slide. Yeah, so this is the answer. You can verify your answers. Okay, now, so for the sake of completion, I have just included these slides. Now we will go to the next topic. Yes, so propositional equivalences. So let's see this. Yeah. Now we have already seen, how to make these truth tables and all these things we have already seen. Okay, that's why I spent the some time in the beginning of this lecture. So basically, if we have if we have some variables, for example a b c d, okay, if we have some variables, okay, then we know that, okay, there are 16 rows possible. Okay, each row actually corresponds to a different combination of truth values for these variables. Okay, now so basically, just consider, okay, let's take only one variable now. So let's take only one variable. So on one variable we know that only two rows are possible. So how many functions are possible? We have already seen only four functions are possible. Okay, f1, f2, f3, and f4. Okay, so one function that is possible is 0 0, another is 0 1, or other is 1 0 or 1 1. You can see there are only, okay, four different functions possible. But if you see what is the property of this function f1, okay, can you observe something about this function f1? You can see that this f1 is always 0. This function f1 is always 0. So basically this function f1 is always 0. Okay, always false. You can also observe the properties of this function f4. So you can observe that this is always true. You can see that this is always true, true or 1, right? But you can see that what are the properties of this f2 and f3? The properties of these two functions are that they are sometimes true, sometimes false. You can see this sometimes false, sometimes true, sometimes true, sometimes false. So these f2 and f3 are sometimes true and sometimes false. So I can write like this: at least one time true, okay, and at least one time false. Okay, so this is the property of these two functions f2, f3. Okay, so similarly you can go to any number of variables. Okay, I have just taken the example of functions on one variable. Similarly, you can go to any number of variables. For example, if you have four variables, then there will be 16 combinations possible, and there will be total 2 power 16 functions possible. Okay, out of these 2 power 16 functions, there will be one function which will be always 0. Okay, which will be always 0. Similarly, there will be one function which will be always 1, which will be always 1. Okay, now all other functions, if you see all other functions, okay, remaining all other for example 2 power 16 minus 2 functions, okay, because this function is always 0, this function is always 1. Remaining all the functions, you will see that they will have at least one row which has 0, and at least one row which has 1. Okay, so now what do we call such functions? For example, if we have a function which is always 0, then we call such function contradiction. Okay, what we call, this is just a name given to such functions. Okay, so basically, if we have a propositional function, or if we have a logical expression that is always false, then that logical expression is called contradiction. Okay, similarly, what is the name given to such function, such expression which is always true? So the name is tautology. Okay, so if so basically, if a logical expression is always true, then such logical expression will be called tautology. Okay, and these remaining functions, or these remaining expressions which are sometimes true, sometimes false, okay, at least one time true and at least one time false, these are called contingency. Okay, so so this theory we have written in this. So basically these are three terms. Okay, so just three terms. Okay, we can see this here. Okay, we can see this here, that okay, a compound proposition that is always true, okay, that is always true, that is called tautology. Basically that is always true no matter what the truth values of propositions. Okay, you can give any truth value to the propositional variables, and if okay it is always true, then such expression is called tautology. Similarly, if it is always false, then it is called contradiction, and if it is neither tautology nor contradiction, okay, then we can call it contingency. Let's take this example. For example, this is actually nothing but one variable function on expression on one variable. So you have two rows. Okay, now you can see this, this expression, this p bar. You can see this is sometimes true, sometimes false. So basically this p bar is nothing but contingency. Okay, this p bar is nothing but contingency. Let me call it cn. In short, I will write contingency with cn. Okay, you can see this expression p disjunction p bar, p disjunction p bar. You can see that this is always true. Since this is always true, hence we can say that this is tautology. I will write tautology with the t. Okay, so basically this expression is nothing but tautology. Similarly, you can see that this expression is always false. Okay, you can put any value of in place of p. You can either put true or you can put false. Basically this expression is always returning false, hence this is called contradiction. Let me write it with c. Okay, so you can see, okay, and these are the different terms, okay, that are given. So a tautology is a proposition that is always true, a contradiction is a proposition that is always false. And we have already seen what is a contingency. Contingency is a proposition which is neither tautology nor contradiction. Okay, now so then before going to the next topic, let's take one example. You can try this example. So let me give you four examples. For example, p implies p. For example, p implies p bar. For example, p bar implies p. Also, p bar implies p bar. Okay, so you have four expressions. I have given you four expressions. Now you need to tell me, okay, whether this is tautology, contradiction, or contingency. Okay, so for each you need to tell, okay, which is okay, which category this expression is, contradiction or tautology or contingency, right? You can write the symbols like T, C, or Cn. T for tautology, C for contradiction, and Cn for contingency. For all the four expressions, these are four expressions, and each expression is a logical expression involving only one variable. Okay, okay, Gayatri, Sanjeev, right? Done. Okay, 1 and 4 are tautology, 2 and 3 are contingency. Okay, so let's check. Okay, so this P implies P. So we already know that we can write it like this. We can write it like P bar plus P, right? Because we have already seen that, P implies Q. How can we write it? We can just remove this implication, and what we can do, we can make it P bar plus Q. Okay, so basically this thing, okay, can be written like this. So basically this P implies P can be written like this, and we know that this is always one. Okay, p plus p bar. This is 1. Similarly, what will be this? This will be p bar plus p bar, and so p bar plus p bar is nothing but p bar. Similarly, this will be p plus p, and this will be p, and this will be p plus p bar, and again this will be 1. So you can see the first and fourth are tautology, because first and fourth expression are true, always true. You can put any truth value in place of p, and the result will always be true. Okay, so since it is always true, hence this first expression and this fourth expression are tautology, and the second expression and third expression are contingency. Okay, so let's move to the next topic, and if there is any doubt you can write it in this public chat. Okay, I am continuously, after every few minutes I am seeing these messages. So if you have any doubt, you can write it here, or you can speak. Let's see the next thing, that is equivalent propositions. Okay, we have already seen actually this concept, because in that example, that roller coaster example, when we were translating that English sentence into logical expression. Okay, at that time, like Sanjeev got one answer and I got another answer. Okay, but we saw that both those expressions were actually equivalent. Okay, so this concept we have already seen, right? So let's just quickly go over it. So we say that if two expressions, so for example, if we have one expression p and if we have another expression q, then we say that two expressions are equivalent. Okay, so this is the symbol for equivalence. So we say that p and q are equivalent if and only if basically truth tables are same. Okay, if we make the truth table for p, if we make the truth table for q, and if both the truth tables are exactly same, then we can say that these two expressions are equivalent. Okay, and the other definition is, we have already seen this double implication, right? And we have seen the properties of the double implication, that this double implication is true when either both are true. Okay, so for example, if this is true, this is true, then this double implication will be true, or both are false. Okay, then also this double implication will be true. So you can see that this double implication is actually true when p and q are same, right? Yeah, either both are true or both are false. So basically in that case, this by implication is true. So this by implication actually, so we can say that p and q are logically equivalent. Okay, logically equivalent if and only if p double implies q. Basically p and this double implication is a tautology. How can you say that? Because assume that they are logically equivalent, then what will happen? Since they are logically equivalent, we know that their truth table will be exactly same. Okay, so if their truth table are exactly same, for example, for p we have truth table. Okay, this, remember, this p is not the propositional variable, this is the expression, this is an expression, and this q is an expression. And let's assume you write their truth table, and their truth table comes like this: 0 1 0 1. Since they are logically equivalent, so their truth table will be exactly same. So the truth table of q also will be same: 0 1 0 1. Now what you can find? You can find p double implies q. So if you will find p double implies q, you can see that it will always be true, right? Because this double implication is true when both are same. You can see that since p and q are logically equivalent, so they will their truth table will be exactly same. So basically, for any combination of the propositional variables, okay, on which these expressions are built, for any combination to those propositional variables, this p and q will always admit the same truth value. Okay, hence you can see that this p double implication q will become a tautology. Okay, so similarly, if we have this p double implication q is a tautology, then automatically they will be equivalent, because we know that this double implication is true only when both are same, this p and q. Okay, so this is the definition of logical equivalent. So we have already seen one example, and we can see few more examples on this. let's see this example. This is the standard example we have already seen many times, and this is a very important expression also. So assume that we have one expression. Now assume that this is one expression. Okay, now this expression is p implies q. Basically this logical expression is involving two variables p and q. Similarly we have this another expression. Now you can just see that if we make the truth table for p implies q, also if we make the truth table for this expression not p or q, then you can see that their truth tables are exactly same, tftt tftt. So you can see that these expressions are equivalent. Okay, so you can write this equivalent sign between them. So basically this expression, okay, is equivalent to this expression. Okay, so now you can maybe try this example. Okay, this is the same example. Okay, let's okay, we have already seen this thing. Yeah, so you can try this. Okay, you need to write the truth table for this, and also you need to write the truth table for this, and then okay, we know what is the actually conclusion, because you know that if p implies q, if this is the conditional statement, then we have already seen that this q implies p is nothing but the converse of this statement. Okay, so this is the statement, and the converse of this statement is this. Okay, now similarly if we have this p implies q, then this not p implies not q is the inverse of this statement. Okay, we have already seen these things in the previous lecture. Okay, so you need to write the truth table for this, you need to write the truth table for this, and then we will check with which of these expressions are equivalent. So you can just try it. If there is any doubt, then you can ask me, because mostly like only 2-3 people are trying, so that's why. If there is any doubt, you can ask me, and if you have any doubt and you are not, you can't ask right now, okay, then what you can do, just learn things, from this point onwards, and whatever your doubt is in the previous lecture or in this lecture, okay, you can ask me after this lecture also. So but focus on the things that we learn, okay, from this point onwards. So okay, now you can write the truth table for this. We have already now not p, this not p. So what is this not p is false. So we already know that this implication is always true except in one case. Okay, which is that case? We know that this case, right? So in this case we can say that this will be false, and in all other cases this will be true, right? So now similarly this q implies p. So this q implies p, again this is always true except in which case, when q is true and p is false. So you can see, okay, this case q is true, p is false. Okay, so in this case you can see that this is false, and in all other cases you can just directly write t. So you can see that this expression, okay, and this expression, you can see that these expressions are equivalent, because you can see that the truth tables are exactly same. So we have established actually this fact in the last lecture also, that converse converse of any conditional statement and inverse of any conditional statement, they are equivalent. Okay, so but we have already we can already seen that this is not same as these two. Okay, this is TFTT and these are TTFT. So you can see that the conditional statement is not equivalent to its converse or its inverse. And we have already seen that any conditional statement is equivalent to its contrapositive. Okay, and what is contrapositive? The contrapositive of P implies Q is not Q implies not P, right? So you can also after this lecture, okay, you can also try to make truth table for this contrapositive statement, not Q implies not P, and you will find that the truth table of this expression will be same as truth table of this expression. Okay, so that establishes the fact that any conditional statement is equivalent to its contrapositive. Okay, so yeah, now now these are the basic laws. Actually these are the basic laws of propositional logic. These are very intuitive, and we have already been using these laws. For example, we have already used De Morgan law and these kind of things. So the first law is idempotent laws. Okay, so and remember that these names are also important, because it is not only, you know, this logic or mathematical logic or discrete maths in which we use these names. In all the subjects you will be using these names. Okay, for example, if you are studying DBMS, then there we have idempotent property and these kind of things. Similarly, in when we will be studying group theory, then also these rules, actually you know, these names, these associative, these commutative, these names will be you know, keep coming. Okay, so basically these names are also important. Okay, and these properties are important. So the first is idempotent law. What is idempotent? Basically, idempotent means if you have P or P, then this is same as P, right? Because P disjunction P, so this is equivalent to P. And how can you prove it? Okay, how can you prove it? You can either prove it like this. You can make the truth table for this, and then you can make the truth table for this, and you will see that the truth table for this will be same as truth table for this. Okay, so but anyway, these are the basic rules, and you must have these things in mind. Okay, so that you don't need to spend time. Okay, so these things must be on your fingertips. Okay, so this is idempotent law. P or this disjunction can also be called or. These things we have already discussed. So P or P is nothing but P. Similarly, P and P is nothing but P, right? Now the next law is so this idempotent law, you will see that basically what is the meaning of this idempotent. You can check out the English meaning. So the idempotent means like this: if you repeat the same thing again and again, for example, P and P and P and P and so on. So if you repeat the same thing again and again, that doesn't change anything. Basically you will get the same answer again. Okay, you can see okay, let me take one example. In the mathematics, in the normal mathematics that we study till 12th class, is this plus operation, this addition operation, is this idempotent or not? Can you answer it? This addition operation is idempotent or not? If this is idempotent, then write yes. If this is not idempotent, then write no. This addition operation, remember this, I am talking about this addition operation is in mathematics, in mathematics that we have studied till 12th class, in general mathematics, like 2 plus 2 equal to 4, that kind of mathematics. Right. So that's why I wanted to clear it, because we are using this plus, we are using in discrete mathematics, we are using this plus for this disjunction operation. Okay, but that's why I wanted to explicitly mention that in general mathematics, okay, we have this addition operation that is not idempotent. Why? Because you can see that if you do same, if you do 2 plus 2, then this is not equal to 2, this is not equal to 2. Okay, so that's why this addition operation is not idempotent there. So I think you have understood the meaning of this idempotent idempotent thing. Okay, so in any subject, it's not only about discrete mathematics, in also in all in many other subjects you will come across this term. Okay, so for example, in DBMS, if any of you has studied DBMS, then in transaction management there is a topic called redo and undo operations. So they are idempotent. Okay, so basically if you keep on doing them, okay, again and again and again, then it does not matter. Okay, so it's let me give you one example. Like in computer we press the refresh button. Okay, so some of us have the habit of pressing it again and again and again. So that kind of thing is here. Okay, so if you just again and again if you are doing the same thing, that doesn't matter, the impact will be same. Okay, so similarly here, p and p and p and so on, the final answer will only be p. Okay, so similarly for this or operation. Okay, so basically we can say that this disjunction operation and this conjunction operation are idempotent operations. Okay, let me give you another question. Is the implication operation idempotent or not? Right, is the implication operation idempotent or not? Yes or no? Right. No. Yes. Yeah. Right. Right. Because you can see that if we apply this p on the both sides, okay, p implies p, then we get one. We get one. Okay, we get one. So you can see that that is not idempotent. Okay. Right. I hope you understood this operation. Why I am spending this much time actually. If you take any discrete mathematics course mostly, then they will not be spending this much time. Okay, they will actually not be spending time in these properties also. But the reason I am spending time is because in all other subjects also you might come across these terms, and at that time you must know that the meaning of these terms. For example, if I say that refresh operation in the computer, okay, refresh operation is idempotent. Let's assume, I don't know if it is idempotent or not, but let's assume that if the refresh operation in the computer is idempotent, then pressing one time F5 is same as pressing 10 times, right? So that's why these kind of things actually keep coming on in DBMS also. You will see these things. Okay, let's see. The next operation is associative law. Okay, what is associative law? So the associative law is basically, if I do this p or q or r. Okay, so basically if there are two or operation in if there are two or operation, then if I do first the first operation and then the second operation, that will be same as doing the second operation then the first operation. Okay, so basically, for example, in general mathematics, okay, when I say general mathematics, then you must think about the mathematics that we have done till 12th class. Okay, so in general mathematics we know that this addition operation is associative. Why? Because you can either add these two. For example, if you add these two, then it will become 5. Then you can add this, so it will become 10. Or what you can do, you can add these two first, and then you can add the result to this. So in both the cases you can see the result will be same. Okay, so you can see addition operation is basically associative in general mathematics. In general mathematics, this subtraction operation is this so tell me, is this subtraction operation is associative or not in general mathematics? This subtraction operation, is this associative or not? Right. So this is not associative in general mathematics. How? Because for example, let's suppose that you compute this subtraction first. Then what will happen? The result will be -1 -5, and the final result will be -6. But what if you do this second this subtraction first? Then what will happen? So basically what we are doing, we are doing the second this subtraction first. Okay, this 3 minus 5, then it will become -2, then it will become 2 plus 2. Okay, so the answer will be 4. You can see that these two answers are not same. Okay, so yeah, so that's why this is the basically this is associative law. Okay, so for you can have any operation. if that operation is associative, then okay, these properties will be satisfied. So for example, in propositional logic, this disjunction operation and this conjunction operation, these are associative. Okay, and so at this point I will ask you the question, is the implication operation associative or not? So basically, what is your question is, implication operation associative or not? You can try this. So my question is, if we have P implies Q implies R, then if we do P implies Q first, for example, if we compute the first implication first and then we compute the second implication, okay, and if I compute the second implication first and then I compute the first implication, okay, this result and this result, are they same or not? So that is the question. For example, if these two things are same, then we will say that this implication operation is associative. Okay, right? So try it. Is the implication operation associative or not? Right, yes. So you can just easily try it. Why how you can also, you can solve it like this. For example, this P implies Q, how can I write? I can write it like this, P dash plus Q, right? And then I can write it like this, implies R. Now I can remove this imply, and what will it happen? This will become dash plus R. So now you can apply the De Morgan formula that we have seen in the last lecture. So the De Morgan formula is nothing but this will become P and Q bar plus R. So this, you can see this is this, and what will be this? This will be P dash plus Q dash plus R. So you can see that this and these are not exactly same. Okay, they may be same, sometimes they may be same, okay, but not necessarily. For example, if R is true, then they are same, you can see, then they are same, okay, but it is not necessary. Okay, you can find some case when they are not same. Okay, so since they are not always same, so we can say that this implication operation is not associative. Okay, so basically, this is the property, this associative law. Okay, this is the property. If I give you any operation now, I can ask you a question. For example, is the named operation commute associative or not? Is the named operation idempotent or not? Okay, these kind of questions. Okay, I will give these questions in the practice set. Okay, now let's move on to the next law, that is commutative law. This commutative law basically says that, okay, if I do P or Q, okay, or if I do Q or P, they will be same. Okay, P or Q is same as Q or P. So basically, this is the commutative law. For example, in general mathematics, we know that addition is commutative. We can do 2 plus 3, or we can do 3 plus 2, both will be same. Okay, but in the general mathematics, this subtraction operation is not commutative. How? Because you can see that this 2 minus 3 is not same as 3 minus 2. Okay, so basically that's the property, this commutative law. Commutative means, if I compute this P or Q, or if I just interchange these operators. Okay, if I put this right hand side to the left hand side, and if I put this left hand side to the right hand side, basically, if I just exchange these operands, then the result will still remain the same. Okay, so this is the commutative law. Now, so in the propositional logic, this disjunction operation and this conjunction operation, both are commutative. Okay, both are commutative. Now, my question is implication operation commutative or not? So basically, you need to answer that P implies Q. Is this always same as Q implies P? That is your question. So implication operation is commutative or not? uh, okay. Gunaskaran, yes, okay. No, actually, this implication operation is not commutative, because we have already seen this, that
But
P implies.
hello,
Okay, are you? Yes, yes.
actually, it will transfer, no?
It will.
Q dash Q dash R P or P dash R
Okay,
Q, right?
let me explain it once, and then you can try. You can see if your doubt is clear or not. Then you can ask me if your doubt is still lingers. Okay. So basically, what I want to say, that implication operation is commutative or not. So if I apply this P implies Q, and if I do this, Q implies P. Okay, now basically I am asking whether these two expressions are always same or not. Okay, so you can see that this is nothing but P dash plus Q. We have already seen this. Okay, P implies Q. This is a very important formula. P implies Q can be written like this: P dash plus Q. Now this Q implies P can be written like this: Q dash plus P. Now you can see that these two are not same. You can see, for example, if Q, you take this case when Q is true and P is false. You take this case, then what will happen? If Q is true, P is false, then this thing will become true, but this thing will become false. You can see that these two expressions, okay, are not are not are not always same. They may be same, they may be same. I am not saying that they can never be same. Okay, they may be same, but they are not always same. And when we say that some operation is commutative, we mean that it will always be same. For example, in general mathematics, this addition operation is commutative. So you can take any
No,
number.
it always different.
Yes, sorry, I did not hear
Yeah,
you.
it always different in general mathematics.
In general mathematics, which is always different.
It won't be equal, no, both the side.
uh,
B
uh,
implies
in
hello.
general mathematics, we don't have this operation. We don't have
Yeah,
this
that's
operation,
what
this
both the side.
I'm not. I'm talking about the addition operation in the general mathematics. The addition operation, like 2 plus 3 is equal to 5. That addition operation I am talking about. So we know that in general mathematics, that addition operation is commutative. So you can take any number a, and you can take any numbers a and b, and then you can do a plus b, then you can do b plus a. You will see that a plus b is always same as b plus a. Okay, so that's why we call addition operation in general mathematics commutative. Okay, so but in propositional logic, in discrete mathematics, this in mathematical logic, this implication operation is not commutative. Okay, so, okay, remember that these fields are different. For example, when I say general mathematics, okay, actually there is no such thing as general mathematics. I am just using that because what I am saying, you can understand what I want to say. That's why I have been saying that the mathematics that we have studied till 12th class, okay, these kind of things, okay. So basically, so you are getting what I want to say, okay, right? But these fields are different. Like this mathematical logic is a different field. Okay, so for example, when fields change, then what happens? For example, if I write this, if on board, if someday, okay, I go to the board and I write this, okay. For example, there is a class, okay, and I go to the board and I write this and I ask what will be the answer. So now, can anyone tell me what will be the answer? Can anyone tell me what will be the answer? Right, yes. So basically, you need to ask me this question, that which field I am talking about, because just by seeing this thing, okay, just by seeing this thing, Okay, just by seeing this thing you cannot answer it. Why? Because for example, if that class if that class in that class, if mathematical logic is going on, or maybe boolean algebra is going on, then the answer will be 1. Why? Because in that case, basically these 1 are nothing but the truth values. Okay, but assume that this same in that class, assume that that class is 8th class or 10th class. Okay, and general mathematics is going on, then the answer will be 2, right? So for example, or maybe uh, binary addition is going on, or maybe binary addition is going on. Okay, so basically in binary addition we know that 1 plus 1 is nothing but 1 1 0. Okay, so you can see that if we change the context or if we change the field, then the answer changes. Okay, that's why actually these properties, for example this associative property, these are not restricted to some field. Okay, you can use these properties in different fields. That's why I've been asking you to tell me whether the subtraction operation in general mathematics is commutative or not. Okay, because basically this commutative thing, this commutative property, this is not restricted to discrete mathematics. This can be used in any field. Okay, in any relevant field you can use it. Okay, so so that's why since we are studying this mathematical logic right now, so basically for us this 1 plus 1 is nothing but 1. Okay, for us okay, this 1 plus 1 is not 2. For us this 1 plus 1 is not 1 0. This is 1. So that's why that's how. So if we change the field or if we change the context, then answer changes, right? So yeah, and the next property is distributive property. So what is this distributive property? So if let's take a journal, any journal operation, for example. Yes. So okay, let me go to some empty slide. Yes, right. So assume that I have two operations. Okay, I have two operations. Let's assume, let me call them hash and dollar. Okay, let me call them hash and dollar. Okay, so now assume that I do like this: a hash and then b dollar c. Okay, b dollar c. Now, so now assume that the distributive property basically says that what I can do like this: a hash b, then dollar, then a hash c. Okay, so basically this is the distributive property. Okay, basically assume that these two things are same. Okay, this thing and this thing are always same, then we will say that this hash operation is distributive over this dollar operation. Okay, so this is the general idea of this distributive property. We have seen the general idea of commutative property. You can take any operation, this is a random operation. This could be anything. This could be conjunction, disjunction, anything, or this could be addition, subtraction, division, anything. So basically the commutative property says that a hash b must always be same as b hash a. Okay, in that case we say that this hash is a commutative. Similarly here this distributive property says that if this hash is distributive, if this hash is distributive over dollar, then we can write this thing as like this. Okay, so a hash b dollar a hash c. Okay, for example, let me again take you to the general mathematics. Okay, in general mathematics we know this thing. For example, if we have two bracket 5 plus 4. Okay, we know that this is here. Okay, this is multiplication. Okay, so 2 multiplication bracket 5 plus 4. Okay, you know that in general mathematics this multiplication is distributive over addition. This multiplication is distributive over addition, and hence we can write like this: 2 multiplied by 5 plus 2 multiplied by 4. You can see that this result will always be same as this result. So we say that in mathematics, in general mathematics, this multiplication operation is distributive over addition operation. Okay, so that is the distributive property. Okay, So now what we can see that in propositional logic, AND operation is distributive over OR operation. Also, OR operation is distributive over AND operation. Okay, for example, let me take one example. In general mathematics, uh, can you tell me if addition operation is distributive over multiplication or not? Okay, so basically my question is addition operation. Okay, addition operation, this is addition operation. A plus b multiplied by c. Okay, is this always same as a plus b multiplied by a plus c? Can you tell me, is this addition operation is distributive over multiplication operation or not in general mathematics? Yes or no? Basically this line, this statement and this expression, they are always same or not? No, yeah, right. So right, Sanjeev, yes, Gunas Karan. So actually, okay, I can't pronounce your name, so don't mind. Okay, I'll ask you what is the pronunciation, and from the next time I'll pronounce it correctly. Okay, so okay, yeah. Guna, yes, Guna. Okay, so basically you can see that in general mathematics, this addition operation is not distributive over multiplication. So basically we can say that this expression is not same as this expression. Okay, but in propositional logic, this disjunction operation is commutative over addition, is commutative over sorry, is distributive over conjunction operation. Also, this conjunction operation is distributive over this disjunction operation. Okay, so in propositional logic, how can you prove it? Okay, I have been giving you these things. You do not need to buy hard these things. You do not need to, just without the idea of how you can prove, you can prove them easily. How can you prove? For example, you can prove this like this. You can make the truth table for this, then you can make the truth table for this. Okay, and you will see that the truth table for this expression is exactly same as truth table for this expression, and hence we can say that this disjunction operation is distributive over conjunction operation. Similarly, you can make the truth table for this expression, and you can make the truth table for this expression, and then you can see that the truth table will be exactly same. Hence we can say that this conjunction operation is distributive over disjunction operation. Okay, now again, I will give you I want to go quickly over these slides, so that today we can finish this propositional logic topic, and from the next lecture we can start first order logic. So now I will be giving you these exercises. In the practice set, I will put these questions. For example, is the implication operation distributive over conjunction operation or not? Is the conjunction operation distributive over implication operation or not? So these kind of things, okay, you can easily I will give you in the practice set. Okay, so let me just quickly go on to the other laws, so that we can finish this propositional logic today. Okay, now this next is identity law. Okay, what is identity law? Identity law basically says that there is an identity element. For example, this p disjunction f is always same as p. We know this. Okay, p plus, basically what we are doing is p plus 0, this is same as p. Similarly, this p plus this p and t is equal to p. Okay, so what we are saying, basically what we are saying that this false is the identity element for disjunction operation. Similarly, what we are saying that this true is the identity element for this conjunction operation. Okay, to give you a familiarity, because we are familiar with our general mathematics. So in general mathematics, we know that any number if you take and then you plus 0, if you add 0, then you will see that we get that number itself, right? So we say that this 0 is identity element for addition. This 0 is identity element for addition in general mathematics. Okay, so that is the same idea here. For example, in general mathematics, what is the identity element for multiplication? You can think it. So basically for multiplication, the identity element is 1. you can take any element, you can take any number, and if you multiply that with 1, then you will get that same element. Okay, if you multiply that with 1, then you will get the same element. So basically in general mathematics we can say that this 1 is the identity element for multiplication operation. Similarly in propositional logic, what is the case? In the case is that this false or 0 is the identity element for disjunction operation. Also this true or 1, okay, these are the this is the identity element for conjunction operation. Okay, and how can you prove it? Again, I'm I keep on telling you, you can easily prove it. You can make the two table for this side, and then you can make the two table for this side, and you can see that this expression and this expression are exactly same. Okay, so they are basically equivalent. Now the next law is domination law. So basically the name itself suggest, okay, the domination. Okay, so for example, if you have p, if you have p can be anything. Okay, if you conjunction, if you apply conjunction with false, then the result will be false. So you can see the domination of this false. Basically this false is like a black hole. Okay, like this is like a black hole. You can give, if you apply the conjunction operation and if you give anything to it, then the result, or the result itself will be a false. Okay, like there is a black hole, you can, if you give anything, if anything goes into this black hole, then it disappears. So something like that. Okay, I'm bad at analogies, so you can just think what I'm trying to telling you. So yeah, so domination law. So the this is like p disjunction true is true. Okay, because if you take any proposition, if you take any expression, if you, or if you take any propositional variable, and then if you apply the disjunction operation with true, then the final result always will be true. Okay, so this is the domination law. Now the some questions could be asked, like I could ask you, the if the for implication operation, is there any domination law? You can you define some domination law for implication operation? Can you try it? Okay, like can you define some domination law for implication operation? Try it. So basically my question is, what should I write here, true or false? What should I write here such that the final result will be that value itself? Okay, so either I need to write here true or false. So basically you need to tell me whether I should write true here or false here, such that the answer is that same value. Okay, yes, Gayatri, yes, Guna, yes, right, true. So basically, if I write true here, then the final result will be true. Similarly, you can try this. What should I write here? Okay, either I can either write true, or I can write false, and so such that the result is basically that value itself. Is there any true or false can I write such that that value itself will come? Yes or no? And if yes, then what is that value? So I hope you understood my question. For the implication, so basically here either I need to write true or I need to write false, such that the final answer becomes that value itself. Okay, Guna is saying false. The thing is that if you write false here, okay, then what will happen? The final result will become true, because this is the property of this implication, that if the hypothesis is false, then the result always is true. Okay, so basically this we cannot put this false, because my question is that if I put false here, then the final result must be false. Okay, that is my question. So false can't be the answer. I hope you understood. Now let's see, Bhavya, true. So let's see if we can put true here. Let's try to put true here. Then what will happen? If I put true here, then I cannot say that final result will be true, because the final result will depend on p. Okay, if p is false, then the final result will be false. If p is true, then the final result will be true. So basically t implies p is nothing but p itself. Okay, so I want true here, but I cannot get true here, right? So we can say hypothetical question. Yeah, right. I'm asking I'm making new questions from these existing questions, and uh, so that you can understand the concept and these kind of things. Okay. It depend upon p, right? It depends upon p. So basically this statement, for this statement we cannot we cannot put any either true or false here. Okay, that depends on p. Okay, so let's move on to the next property, that is double negation. What is double negation? So if I have a proposition p, then I can apply the negation and I can get a proposition p bar. Then if I again apply negation, then the final result will be p itself. So basically if I double negate something, then I will get p itself. Okay, so this is a very intuitive property. Now let's see this complement law. What is the complement law? So basically this is the complement law. Basically if you p conjunction not p, okay, that is false. Okay, similarly p disjunction with not p, that is true. Okay, so basically okay, these are not that important laws. These are the, you can think of them as properties. Which of these laws are important, like the names itself? So basically these laws are important. For example, idempotent law, this name itself, okay, is important. Similarly associative law, commutative law, distributive law, these four laws are important. Okay, these names are important. You must understand the meaning of these laws, so that in any subject you if you come across these laws, then you can you can know. Similarly this identity law is also important. Okay, and this double negation law. So basically this domination law, this complement law, these are not that important. You can, if even if you forget the name of for example this property, if you even if you forget the name of this property, then also it is fine. Don't worry about that. Okay, but you should not forget the name of this property. Okay, if you see this property, then you must immediately think, okay, this is the identity, this is the identity property, this is the identity law. Okay, so yeah. Now next this de Morgan law we have already seen in the last lecture, so I'll skip this. Okay, so this is the de Morgan law, we have already seen this. Now this absorption law, basically this is again, this is not so much important law. This p or p and q is basically p. Similarly, basically how can you prove it? You can either prove it using truth table, or what you can do, you can see that this is distributive. We know that this disjunction is a distributive over conjunction. Similarly we know that this conjunction is distributive over disjunction. Okay, so what you can do, you can also apply this distributive property, and then also you can solve it. Let me solve this. Okay, p or p and q. So how can you solve this? So p or p and q. Okay, let me take another slide. P or P and Q. Let me take this slide. Yeah, right. P or P and Q. So what? Since we know that this or is distributive over and, so we can write it like this: P or P. Okay, actually we will get the same thing again. Okay, so yeah, right. So we will get the same thing again. P or P and P or Q. No, so this P or P will become P. Yeah, right. This will become P and this will be P plus Q. So basically we started with this expression, and then we got this expression. Now basically if we again try applying this distributive property, then we will get this expression. Okay, so this way we cannot solve it, but yes, you can solve it like this. For example, you can solve it using truth table. Okay, or uh, right, yeah, so you can solve it, you can prove it using truth table. Okay, I think we are stuck here. There is a method I'll see, and in the next lecture I will show you the proof of this without a truth table. Okay, but for now you can prove this using a truth table. Okay, let's see. Yeah, right. So all these properties are over. Yeah. So these are not that important. You can just go through these properties. The important properties I have already discussed, like the De Morgan law, associative law, commutative law, distributive law. These are the identity law. These are the important ones, and all others you can easily see and you can easily prove. This we have already seen, like P implies Q. This we have already seen, so I don't need to go into this because we have already seen this many times. And this, yes, this is important, and this we have already seen, because this P double implies Q, basically this is nothing but P implies Q and Q implies P. So this is also we have seen in the last lecture itself. Okay, so let's go, let's move forward. Now this again, I have already we have already seen that if there are n variables, then there will be 2 power n rows, and how many functions will be there? Functions will be 2 power n. Okay, so these things also we have seen. Now the next slide. So like we need to show that these are equivalent. So we have already done some exercise. So if we have this expression and if we have this expression, then you can you say that these are equivalent, logically equivalent or no? So how can you show this? You can make the truth table for this, you can make the truth table for this, and if those two table are exactly same, then we can say that they are logically equivalent, else they are not logically equivalent. But without truth table, how can we solve it? Let's solve it. So without truth table, how can we solve it? This, so basically the first expression is this. Okay, not P implies Q. Now this P implies Q, I can write like this: P dash plus Q. Okay, and this now this, so basically this is the De Morgan property, right? Because this is the P bar plus Q whole bar. I can remove this from here and I can write like this, because so basically P bar plus Q whole bar. Now this is the De Morgan property, and we can write like this: P and Q bar, right? So you can see that we got P and Q bar, and the second expression is also P and Q bar. So you can see that both expressions are equivalent. Okay, so so this is the first example, and this is the second example. P and Q implies P over Q. Okay, we need to show that this is tautology. So how can you prove it? You can make the truth, there are two ways. Either you can make the truth table for this, and but the thing is that truth table takes time, because for example, if you have two variable, then there will be 4 rows, you need to compute 4 rows. Okay, so without truth table, you should try to prove it. So okay, I'll give you 1 minute. Without truth table, using the property, which property? Either De Morgan property or this property that P implies Q is nothing but P dash plus Q. Using these properties and De Morgan property, you should try to show that this expression is always true. Try it. Guna P or Q plus P or Q. No, you have not applied this De Morgan property clear properly. Let me try it. Okay, you can check. So we have P and Q implies P or Q. Let's see. So let's see how all the empty slides are over now. Okay, let me try it here. So basically, the question is P and Q implies P or Q. So we already know that we can remove this implication, and when we remove this implication, then this will become dash and this will become plus, right? So we can write like this will become plus. Now here we can apply the De Morgan property, and that De Morgan property says that this and will become or. The De Morgan property says that basically this and will become or, and this p will become q bar, this q will sorry, p will become p bar and q will become q bar plus p or q. Okay. Now so basically we have this p bar plus q bar plus p plus q. Now we know that these all are plus. Okay, so basically we got p bar plus q bar plus p plus q. Then what will happen? Plus q. What? So now we know that this p plus p bar it itself is true. We have seen this p plus p bar is true, and anything plus true is also true, so we got true. Okay, so this p plus p bar is always true. We have seen this thing. Okay, also we have seen that true plus anything is true by that domination property. Okay, so finally we got a true. So basically this expression is always true, and since this expression is always true, hence we say that this expression is tautology. Okay, so so this is tautology. Now let's see what we have skipped. Okay, so this is the solution. This is the solution. We have already seen this. Now the next is this tautology, contradiction, contingency. We have already discussed this. Okay, so this slide actually this is a redundant slide. We have already discussed this thing. Now the next topic is satisfiability. So the next concept is satisfiability. Okay, these things also we have already discussed. Okay, so these are also redundant slides. So basically if p and q are then this is tautology, this is contradiction, and all these things. An expression is tautology if and only if in the truth table we have in all the rows we have basically one value, one truth value, one. Similarly an expression is contradiction if and only if in all the rows we have the truth value 0. Okay, and an expression is contingency if and only if in at least one row we have 1, and at least one row must be there which has 0. Basically contingency means neither tautology nor contradiction. These things we have seen. Okay, now the next thing is satisfiability. Yeah, propositional satisfiability. So this is also very easy concept. So basically if we have some expression. Okay, if we have some expression, let's assume that we have some expression f. Okay, then we say that that expression is satisfiable. Satisfiable means somehow you can satisfy it. Okay, and by satisfy it I mean somehow you can make it true. Okay, so basically an expression is satisfiable. Okay, satisfiable means somehow you can make it true. Hence we can say that for some, so basically this expression some this logical expression f, this is satisfiable if and only if for some combination, basically for some row we must get value 1. Okay, so for example if we have seen that this p and p bar. Okay, what is this? We know that this is contradiction. Why? Because this is always false. Okay, so we can see that this p and p bar, let me denote it by f dash. Okay, let me denote it by f2. Okay, f2. Okay, so this is f1, this is f2. So this f2, which what is f2? F2 is p and p bar. So we say we can see that this f2 is always false. Okay, so there does not exist any row for which it is true. So we can say that this is unsatisfiable. We cannot satisfy it. Okay, we cannot make it true. So satisfiable. So an expression is satisfiable if and only if we can make it true for some combination, for at least one combination. If we can make it true, then that expression is satisfiable. So basically we know that contradiction, if some expression is contradiction, then that can never be satisfiable because we can never make it true. Okay, but if some expression is tautology or contingency, then that expression is satisfiable. Why? Because tautology is always true. Okay, we only need to find on one row which is true, but tautology is always true, so for all rows it is true. Similarly contingency, the definition of contingency is that for some row it must be true and for some row it must be false. So that row for which it will be true, that row satisfies our expression, so we can say that that expression is satisfiable. I hope it is clear. Basically an expression is satisfiable if and only if for some row in truth table we have truth value 1. Okay, we have truth value 1. uh, Bhavya is typing. Okay, is time is over, right? But let me quickly complete this satisfiability part. So yes, so if an expression is satisfiable if and only if for some combination it is true. Okay, and similarly unsatisfiability. What is unsatisfiability? An expression is unsatisfiable if it is always false. Basically we can never make it true. Okay, so we can say that satisfiable means either tautology or contingency. So this is what I have written. Okay, satisfiability means either tautology or contingency, and unsatisfiable means contradiction. Okay, so if some expression is contradiction, then that expression is unsatisfiable, and if some expression is tautology or contingency, then that expression is satisfiable. So I have written this thing. Satisfiable basically means that either tautology or contingency. Unsatisfiable means contradiction. Okay, now again these terms also. Tautology means always true. We know that tautology means always true. So basically tautology is equivalent to being true. Okay, being true, being always true. And also this term like valid. For example, if I give you some expression f and if I ask you if that expression is valid or not, that means that expression is tautology or not. Okay, for example, if I give you this expression p or p dash, okay, is this expression valid or not? So we know that this is tautology, hence we can say that this is a valid expression. Okay, so this valid, true and tautology, these are similar. Similarly this unsatisfiability and contradiction, these are similar. Similarly this satisfiability means either tautology or contingency. Now invalid means not valid. Okay, so basically we can say invalid means not valid, or we can say not tautology. Now something which is not tautology can either be contradiction or contingency. We know. Okay, we know that if you have n variables, then you have 2 power n functions possible. Okay, now for from out of these functions we know that exactly one function is tautology, exactly one function is contradiction, and all other functions are contingency. Okay, so invalid means not valid, not valid means not tautology, and not tautology means either contradiction or contingency. Okay, I hope this terminology is clear. Okay, so okay, this again is we have already seen this thing. Now so this topic is over, and this satisfiability. So we will end today's lecture here, and I hope you got it. But if you have any doubt, okay, slides will be shared. Yes, slide will be shared. Notes I have already shared, and I will keep on sharing the practice problems. So for the last lecture, I have already I've already shared the practice problems, and for this lecture also I will share many questions, around maybe 30 questions I will share, and you can attempt them. So mostly the propositional logic, mostly it is over. Okay, some things are remaining that we will cover in the next lecture. Okay, and in the next lecture we will also start first order logic. That is important, and that is non trivial. Like propositional logic is easy. Okay, this is a easy part. You will also study these same things, or you will study in boolean algebra also, in digital logic or computer organization. In that course also you will study these things again. Okay, so yeah, so the next lecture is very important. First order logic we will start, and so if there is any doubt, then you can ask me right now, and or you can ask me anytime. You can either message on the group, or you can even message me individually, and you can ask me any doubt from any subject. You can ask me. It is not a necessary thing that you ask me only from this discrete mathematics. You can ask any doubt, and if I will share practice questions. Okay, you can go now. Time is, yeah, we have already crossed 5 minutes. So actually and do give also, so one I want to tell you one thing. do give your feedback, because after the first lecture you gave me feedback, and I have tried to consider that feedback, and I have tried to better myself. So I have just completed this mtech, and that's why this is my teaching experience, this is my first teaching experience. Okay, so I want to give you all the quality, all